Everyone, welcome back to the second part of sorting algorithms. Today we are diving into two super important sorting algorithms, quicksort, merge sort. These are foundational concepts in computer science. So let's dive into it. As we discussed earlier, sorting algorithms are used to arrange elements in an array in either ascending order or descending order. Quicksort and merge sort are among those efficient sorting algorithms with an average time complexity of big O and log n, but they work in a different manner. So first, let's start with quicksort. Quicksort uses a divide and conquer approach. So how it works? Let's imagine this array. So first we pick a pivot element. This can be any element, but usually we take it last element. So here 4 is our pivot element. So next we will divide this array into two different parts. One smaller than 4 and one bigger than 4. So 3, 2 and 1 will be at one side. 4 is our pivot element and rest 7, 8, 5, 9 and we have two 5, so again 5 will be at one side. So now as our array is divided into two parts, we will again check for pivot element in both these arrays. So here in this one we can consider one as our pivot element, and then we will again divide our array into two parts, and here we can consider 5 as a pivot element and divide it into again two parts. So we will repeat this process for the left and right subarrays until the entire array is sorted. So like here it's 1, it can be divided into 2 and 3, 2 and 3 together because nothing is smaller than 1, and here it's 5. So since there is one more 5, it will be on left side, and 7, 8, 9 will be on right side. So let's do the code for this. We will first define a function quicksort with a parameter array. Then n is the length of our array. So here this means it's the like a base case that the if array has one or no elements. So such arrays are already sorted. So no need to further sort this array. It will directly return the array. But usually we don't have these arrays. So in the else part we will do our quicksort algorithm. So first let's initialize our pivot element, that will be the last element of the array. Then we have three parameters: element for less than pivot, element that is equal to pivot, that is pivot only, and then el- elements that are greater than pivot. So let's define all these. At the end, we divided our array in three parts, and at the end, we will return all the three parts together so that our array could be completed. Now let's take any array, for example, 4, 6, 2, 8, 7. Let's print our array with quicksort implementation. As you can see, the array is sorted. So what we have done is we have first chosen the last element of our array as pivot element. Then the algorithm recursively applies the same process to the subarrays formed by elements less than or equal to or greater than the pivot element. Then the final sorted array is obtained by concatenating the sorted subarrays. So quicksort is fast and uses less memory because it's an in-place sorting algorithm, but it can be inefficient for already sorted or nearly sorted data, leading to its worst case time complexity of big O and square. Now, let's talk about merge sort. It also uses the same approach, that is divide and conquer, but in a slightly different way. So let's understand with the help of an example. So this is our array. We will first divide our array into two halves until each sub-array just contains one or two elements, and then we will merge these smaller arrays back together to a sorted array. So here let's first divide it into two equal parts. Let's take these 4 on one side and these 3 on one side. So these are the two subarrays. Then again we will divide and take 38 and 27 on one side, 43 and 43 and 3 on one side, 9 and 82 on one side, or 10 on one side. Then again we will divide it until we obtain every like single one element in each array. So like for our final will be like this. We have divided it. Now let's do the merging. So if we first do the merging of these two elements, it will return 27 38 after sorting. Then these two it will return 343. First 3, then 43. This will return the same 9 and 82. And let's keep 10. Hello. Now we will again merge these elements. Now these four elements. So it will be 3, 27. Pardon for my writing. 3, 27, 38, 43. And we will combine these. This is one array and this is another. So it will be 9, 10, 82. Now these two are our sorted array and we will merge these two both. So it will be 3, 9, 10, 27, 38, 43, and 82. So our array is sorted. First we will divide the array and then we will merge it. Now let's see the coding part of this. Uh, Implementing merge sort in coding is a bit like lengthy and not complex, it's a bit lengthy. So let's do it. First we have defined our function and then n is length, and then let's find the middle element. And after finding the middle element, we will divide our array into two parts, that is left half and right half. Then we will perform a merge sort in both of this left half and right half. Now initialize our variables I, j, k as 0. And now we will run loops to sort this array. So what we have done in this loop is that we have used I and j to track the current index of our left half and right half array. And then we compare the elements from both halves, and then we will insert the smaller one onto the on into the position of A. So after inserting next, let's run our next loop. So what we have done in this is that let's write the similar code first for J also. So what we have done is if one half is exhausted, we will copy the remaining elements from the other half. So this is our code, and now let's give a source like example of an array. Let's imagine this is our array and then we will let's see if it's getting sorted or not. So as you can see, our array is sorted. So merge sort is stable and guarantees big Go and log and performance, even for worst case scenario. However, it's not an in-place algorithm, meaning it requires extra memory to store temporary arrays that we make while dividing. So let's conclude our video here. A quick difference between both, that quicksort is great for in-place sorting when memory is limited, but it's not ideal for sorted or nearly sorted arrays. Merge sort is stable and reliable, making it better for large dataset where consistent performance is crucial. I will attach the code for the same below in the description. Thank you.